Welcome to this Math Subject Knowledge Enhancement webinar on further trigonometry. Before we get into trigonometry, we're going to start by just checking how you are about the assignment and running through this. I was going to say again, but then I can't remember whether I have been through this with you or not. This is I've just, copy and pasted off the guidance document. Just to sort of clarify anything, and in fact pitch in at any time, because I'm not really sure where you guys are. In fact, where are you guys with your assignments? Has anyone started their assignments?
I started mine last week and I'm presenting it next Thursday.
You're presenting it?
Yeah. I fully intend to be making significant revisions after the presentation based on the feedback, and obviously handling it in line with the deadline. But I'm working on it. I started working on it last weekend, and I'll be hopefully getting it finished over the next week and presenting it at our staff meeting on Thursday afternoon.
Okay. So that's the thing. So it says during the spring term, this term, you will be presenting whatever it is that you write. So 15 minutes, and depending on who it is, could be your department, but might not be, so be clear. And the feedback sheet is essential, so you need to give them each feedback forms, because that needs to be included with your assignment. That's your evidence for your assignment. I'm guessing you'll need to scan them in, or obviously what you could do, if you do it before I see you at the intensive study week, you could give them to me. However, you will probably need to keep them because you'll still be doing your assignments. So, scanning them is fine.
Can I ask?
Yeah.
Can I ask a quick question?
Yeah.
I was going to do mine on growth mindset within mathematics. Is that all right?
Absolutely fine. Yeah, absolutely fine.
Good. Because seriously, I am actually giving it on Monday and I've not started it yet.
Are you presenting it on Monday?
Yeah.
Wow, okay, have fun with that.
Yeah, cheers.
You're my hero.
I'm scared. I haven't done anything. What is growth mindset?
I've done the growth mindset presentation with you though, haven't I?
Yeah, I'm still in that.
Yeah, that's fine.
Sorry, I just wanted to check that I could do it on that and then write about how that makes me better at teaching.
Yeah. Have you used it in any of your teaching? Because so it's either, because sort of here. No, I want to go this way. Either you can select one theme and talk about it, so it could be viewed as a theme, or it could be one of a resource. It depends on how you've done it, I suppose. But yeah, I think as a theme is absolutely fine. In fact, one of the guys last year did it, but he did it as one of his resources, and actually it was he had too much stuff. So yes, the growth mindset is absolutely fine.
Thank you.
Bowler, Dweck, all those people, and there's a lot, and there's a growth mindset maths that Helen Hintel, the website she's done. Hopefully it should all be on my presentation that I did before.
Thank you very much.
Right, well, good luck with that. That'll be fun.
Yeah.
But I suppose the presentation itself, of course, although there is feedback which will be put in. The reason that the feedback's being put in is so that you can't just turn up and say whatever and expect to get away with it. But because you're then later going to make it better. But it doesn't really matter. I mean, the fact that, of course, it's the people who are seeing it are not marking it. So, that'd be nice. Yeah, so it says then reflect the feedback, add comments. So Will and Adam are on their way. Alex, do you know what you're doing?
Yeah, well, I'm going to do, I've got a really low ability year 7 class, so I'm going to try to do something that I'm promoting progress with low ability students, but so carrying out the experiment, if you like, with that class.
Mm-hmm.
So I think they are the lowest ability year 7 set 3 class the schools had in the last 4 years, and they've given them to me. So I've got a boy in there with cerebral palsy, etc., etc.
Yeah.
So it was all about getting strategies in which, and they're all at sort of targets are level 3s, so really low, and it's trying to get them strategies that work in order to see progress developing over a period of time. Now I've tried loads of different things, but my problem is I'm trying to get literature now to back that up, and then I'm going to feed back to the department on the week after the break, which is the intensive study week.
Yes.
I won't be coming to.
Oh.
Because of an issue up here, but I'm still waiting on clarification of Karen. So that's another issue. So that's when I'm meant to be delivering it back to the school.
Okay.
My presentation. But I think that gives me enough time to get the feedback from them.
Yes.
And then
just about.
Even act on and then act on a couple of things, because I see them 4 times a week with class as well.
Right.
And feedback on maybe some changes that I've did regarding the feedback, and then and include that as well.
Yeah, I mean, ultimately, it doesn't matter if everything you've done is rubbish, as long as you critically analyse that.
Right. Okay.
So, you know, even if they've all completely failed to progress, you can say that is because of, you know, whatever it is that you didn't work because of this theory, and you know, and so on, you know, so, or that it had an impact for a few lessons, and then they're like goldfish, so their memories were wiped, and you start the week afresh again, you know, yeah, and so then you could say, oh, so maybe I should try Dylan Williams interleaving, and so, you know, just find something else you could have tried or something if it doesn't work. Oh, so that's a shame. So I realised that the intensive study week is the last time I'll see you, possibly.
I can come down and visit you. You know, have a cup of tea. I'm always in that neck of the woods.
Are you free to babysit?
We don't want any
What did you say?
What was that, Jerry?
I said we don't want any blubbing.
No. What, from me? I don't know.
I could always hold a webinar.
From any of you.
We can hold a webinar.
Oh, yeah, and I've got to see you. There are other webinars. So we've got, supposedly we've got two more webinars anyway in the summer term. Not supposedly, we do have two more webinars in the summer term. And there's supposed to be some sort of review thing at the end. Last time, you know how it is, we were given such short notice, and it was on a Thursday evening, and I was just like, well, obviously there's no way that I can do that. So hopefully they might give us some more notice. However, have any of you received any information about the intensive study week yet?
No.
Me neither.
No,
It's just at Bristol, isn't it?
I can only assume. Yeah, that is all.
But we haven't had like the booking thing that we always do or anything like that, so it's a bit.
I know. I'm going to chase that up because I have a feeling that maybe Susie's left or something. But the yeah, it's all very quiet. It's a month away. Yeah, normally we have a thing where we say, you know, which nights we're staying and stuff. We have. But anyway, so hopefully I see the rest of you there.
I think we've got to stay for more nights.
Oh, yeah. Whereas I,
Sarah?
Yes.
It hasn't been confirmed that I can actually take that you know, that I've got permission to not go to that and continue on the course.
Right.
But I have I've not gave them the ultimatum yet, but I said to them, look, there is no way I can go to that week, and if it comes to it, I'll have to come off and defer and then come back on next year.
That's ridiculous, isn't it? So the, you know, I suppose it's personal reasons to just sort of say that, and you know, from the subject point of view, we are going to be doing.
Alex, I missed it. Oh,
Yeah,
I missed the whole chunk, including an intensive study week for medical reasons, and no one's batted an eyelid. If there's a good reason, then it can happen. And if necessary, waive the I'm a maths teacher card, and you can't afford to chuck maths teachers away.
No, quite.
That's pretty much.
Right, okay, thanks for that.
Yeah, Jerry's going to find this is a slightly trickier webinar, having missed the one that came before, the intensive study week that came before for this, that we did last year. But I'm sure you'll manage. But at the next intensive study week,
I just say no cuff too tough.
Meh. At the next intensive study week, we're going to be doing decision maths, which is a discrete module at AS level, which I don't imagine that you're going to be teaching anytime soon anyway. Definitely not to your year 7s. So, and we're basically going to be working through this pack that I've created, which is fairly extensive, which I can send to you.
Please do.
Yeah, and otherwise, so from my perspective, when you're not really missing anything, and the reason for that is because during last year, that's when they did their presentations for their assignments. So I hadn't originally planned anything for it, so it's kind of an extra anyway. Yeah, I'm not concerned from my perspective, but obviously there is the whole rest of the week of stuff. You know what else there is, but they won't. I think they'll be fine. But yes, but in the summer, I think there is supposed to be some sort of thing that I'll try and get to if they give me enough notice. Anyway, moving on.
It's supposed to be 13th of July. I think it's only for a couple of days. It's supposed to be like, this is how you become an NQT now or some rubbish.
Yes, exactly. And I didn't go to the last one, and I wasn't even invited actually. So I would guess that I'm definitely not needed. I would, you know, there's no, you're not doing any teaching or anything. But it'd be nice to see you guys off. And yeah, last time they sort of said, you know, how we always do like the Tuesday, Wednesday sort of finishes by the end of the week, sort of pieces off. Instead, they did it Thursday night to Friday, which was a bit weird. So who knows? We will see. Anyway, so it looks like most of you are on track, apart from Joe, who has not started his assignment. So Jerry, if you've got any issues with it, please feel free to ask, but you're basically just supposed to be picking something, whatever it is. Where are you at the moment, Jerry? Are you in school? Are you still in this special school?
Yeah, I am. No, I did that for my alternate placement, and I've now got a new mainstream school, far better than the one I was at.
Great.
The schools are similar, apart from it's now mixed, but the leadership team is a breath of fresh air. They are a leadership team, whereas the last lot were just a bunch of toxic wasters. So yeah, I've never been off the course. I don't know where that came from in your email. I've always been here.
Yes, no,
in terms of my assignment, I'm still thinking of the girls in maths conundrum.
Well, and also you now have it to compare against your mixed school.
Yeah. Yeah.
So you can draw some
where strangely enough, having encountered some appalling maths ability and aspirations and attitudes at your girls' school, I've now come to this mixed school where in a lot of my classes it's actually the girls that are at the top edge set.
Absolutely, absolutely. So there's something about when it's all girls together that that negativity. I suppose it's a it's a it's a typical confidence feature of girls. You know, they do this sort of I don't know, bitching and moaning about things. That in a mixed class, the boys they don't let that continue. It just doesn't happen as much. And thus the sort of the girls are then like, oh right, okay, we'll pull ourselves together, we're going to beat you. So yeah. Well, it'll be interesting. I will look forward to reading whatever it is that is produced by you guys. And it's due on the 14th of where was it now? Due on the 14th of March, a bit randomly. It's a Monday. I assume it was like, oh, let's stop reading on Friday so that they get the weekend. But seemingly arbitrary. So yeah, email me if there are any issues with it. And otherwise, let's move on. So a little bit of theory today is about language and just a bit about things that the students find difficult to understand, because the problem with solving a maths problem is it's not just as simple as, oh, here's what the issue is, let's solve it. You've got it written in some completely weird language. They have to interpret what it's saying, do the maths, and then write it back in math language. So a lot of the time with the teaching, we're focusing on the process so that they're absolutely able to do, I don't know, equivalent fractions, whatever. But once it's within a whole problem, they don't realise that that is what they have to do, and they really struggle. So you can get kids who in class have just got, books of beautifully written problems, the short questions where it's just like, do this, do this, do this, do this. When it doesn't just say, do this, they don't know what they're supposed to do. So yes, and often long, complicated, you see all sorts of crazy spelling things. And words that have everyday meanings that can mean something different in maths. Like when we talk about similar triangles, and all sorts of things where to us similar in the English language means quite like something else, whereas in maths it actually means exactly the same as something else. So that's rather tricky. Also, not congruent. It means in the same ratio to it. And then, Alex, were you going to say something?
No, sorry, I just coughing in the microphone. Sorry.
Oh, sorry, you just not muted that. So yes, symbols and graphs and that sort of thing is always difficult, and I'm sure you'll probably come across the fact that a lot of students think that A is for apple, it's like a thing rather than a variable, and the conceptual difficulties they have later on is that they've got this fixed idea of what it is. They can't appreciate that it is anything and can change, and yeah, get stuck with understanding what algebra is. So yeah, so teaching math is not just about teaching the processes. Obviously, there's all the language side that goes with it, and encouraging them to be able to read and write math language. So, I mean, there hasn't been really a big push on maths literacy at all, as far as I'm aware. But just generally within your teaching, good ones to do a mini whiteboard, guess who's, where you've got, one student draws a quadratic graph on their whiteboard, the other one has to ask questions to figure out which graph it is. And then you can put words up on the board they can't use, so they're not allowed to say the word vertex. Well, they can't say U-shaped or N-shaped or whatever, and you're trying to get them to say parabola, and you're trying to get them to say vertex and that sort of thing. Or if one of them's, drawn, could see something, and they, when the other one's construct it. Oops. So yeah, it also gets that sort of need to be precise. And then mathematizing, so taking an actual written English problem and putting it into maths notation. Obviously, if you can't do that as you get towards A level, then you're going to struggle as you get towards university and any sort of engineering or any applications. You want to solve a problem. It's going to be a real life problem that someone's going to come to you and saying, "Oh, I want my computer to do this." You need to be able to translate that into math. So yeah, just sort of some ideas. I put these short writing prompts. So just get them to write. Don't necessarily. It's very difficult, isn't it? Because when I was taught, they'd write out on the board a whole load of notes for us to write. That's kind of gone by the wayside, and it's more about sort of writing the process down. Whereas we had to write these notes, and then later, as we sort of got older, they would tell us stuff and say, "Now write notes about what I've said." And that is something that students are really lacking in nowadays, this ability to write their own notes, actually write down what was important. So, one of the things you can do is that rather than just giving them a homework to test, their process, say you want them to go away and write up some notes about what you're doing, and then you'll take it in and see, check the notes they've written and they're all right, rather than just a homework. And then there's left out reference for that. Right, trigonometry. We did this last year when Jerry was off at the intensive study week, and we basically just did the basic trigonometry. And actually, I've got a lot of slides, so I'm going to skip over this bit. But that could be quite a nice one to give kids. So a 3-fact triangle is where where 3 out of 4 facts. No, 3 out of 4 of these facts are true. And they have to, try, and they can construct them, they can draw them, they can try and figure it out. And actually, there's quite a few of them, as you can see. That's a nice starter for just when you think about it, but we'll move on. So last time we looked at the basic trigonometric ratios, the SOHCAHTOA. We looked at the sine rule, cosine rule, area. There's a little bit about special angles. Very briefly mentioned radians. We'll look at that again. And we did sectors and a little bit about trigonometric graphs. So Jerry, because you missed it, the first question is to you. Which of those, if any, do you not know?
I've covered them all as part of my self-study, and I remember most of it from the things that I had to look up again were the sine and cosine rules, radians I've used extensively. I'm not sure what you mean by special angles, but I'm sure when you mention them all, I'll recognise them.
Yeah, I'm going to go over all of it very briefly now. Well, I'm not going to go over SOHCAHTOA again. Has anyone taught trig ratios?
I've just been doing it this week with a guy that's as lazy as, but he's got he had last weekend an entrance exam for a selective sixth form, and he was going for a bursary. And when I asked him what the requirements were for all these things, whether there was an interview, he knew nothing. And actually, I was asked to do it, thinking that this would be later in the year. So I started last week, did the first session with him, and said, "So when's your exam?" "Saturday."
Oh.
Right. You haven't got a lot of time then, and you don't really know very much, given that this is a competition. But there we go. Yeah. So I covered quite a lot of stuff on that list there. In that, well, I did 3 sessions with him again. Found him in.
Oh well, hopefully you'll be really good in other areas. Yeah, Will, have you taught this?
Yes, I haven't taught sine rule, cosine rule, but I did have to go. I did went and revised that, thinking I might be teaching it, and then my timetable changed. I ended up doing a different thing, so I'm familiar with all of it. I think special angles, that's all the ones, the trig ratios that give you nice whole numbers or easily expressed.
Yes, yeah.
The ones that they now have to learn as part of the GCSE.
Yes, they do. exactly.
Are you talking about 3, 4, 5s and 5, 12, 13s and that sort of thing, or are you talking
No.
about?
No,
No,
sine,
geometry.
cosine, tan, 30, 45, 60 and 90.
Yeah.
Okay.
We're going to look
All
at
right.
it. We're going to look
Yeah,
at it
happy
in a
with those.
minute. Yeah, I've got it. I've done them again anyway on here. So we'll have a quick look at some of these. So, quick reminder, and this is the thing, sine and cosine rules and the area, you don't use very much. It does come up at the very top of GCSE and it comes up again in AS level. And the students in both, so they used to be given this in GCSE, but now they have to learn this off by heart. It's one of those things that, well, I must have done at GCSE, and I couldn't remember for the life of me. When I came back to teaching it, I was like, really? Gosh, I don't remember this at all. Will, can you just mute your mic, please? So yeah, it's one of those things that, you know, it's easily forgotten. They don't do very much. So those are the sine and cosine rules. I'm sorry that this is on a different slide. But if you just want to have a go at doing this, using them, do you want me to write them along here? If I really badly. So, Will, I've just muted you at the moment, so if you want to talk, then I will unmute you. So, for this triangle, find the lengths of BC and AC and the area. So, the sine rule, I will write up here. It's often written as 3 bits, but really it doesn't matter. All it's saying is that a side over an angle opposite it is in the same ratio to any other side and the angle opposite it. So that's the sine rule. And you use the sine rule when you've got 2 angles and a side, or 2 sides and an angle. And then the cosine rule you use when you've got 2 sides with the angle in between, or all 3 sides. Common mistake, which I was nearly about to write, was to put just to automatically write sine there by mistake, because it's not consistent. And the area. So the 2 sides and the angle in between. All of these letters are in fact not the same and are completely arbitrary, depending on how you label your triangle. So I'm going to do this now. And put your hand up when you've done that. Is your hand up because you've done it already, Alex? Or do you have a question?
No, I've done it.
Oh, good. That's quick.
It's all wrong, but I've done it.
Yeah, if you don't have a calculator for this session, you're going to find it quite tricky.
Do you know something? I've got a story about calculator.
Okay, go on then.
I bought myself a calculator because last time somebody stole my calculator at the other school, so before the last webinar, so then I got myself a calculator, a bright blue one, kept it, pride and joy. Last night, come home from school, get everything out for today's webinar, calculator's not there. I'm like, oh my god, I'm just not going to turn up for the webinar because she's going to go nuts. Just not going to do that. And then I phone round everybody and someone has given me a calculator. It's 25 years old.
Is it solar powered?
A sharp scientific. As she said, it's 25 years old. I am struggling with the buttons, but I think I've got it.
A sharp one, is it, did you say?
A sharp advanced DAL EL531LH.
Yeah,
I
similar
think it's an
to
antique.
like similar to
Well,
that.
mine is older than that.
Yeah, this is fairly new.
Mine doesn't have those sort of.
It doesn't have the arrows.
Mine is square.
Yeah. I hate this calculator. I don't know why I bought it. Well, I do know why I bought it. It was cheap. But versus Casio, I'm definitely much. Sorry. Right. So just waiting over to. Well, we'll get started on it. Who would like to talk me through what they did first? Who did first? Okay, well, okay, go on,
The
Will.
obvious thing to do first is to work out what angle A is, which is
Yeah.
just 180 minus 118 minus 26.
Yeah. Which gives you,
Which is 36 degrees.
okay. And then what did you do next?
Well, then I worked out what side AC was, because you've got, you know, the side opposite angle C, and you know angle of B, so you can work out BC, which would have been 16 sine 118 divided by sine of 26, which is 32.2 to one decimal place.
Okay.
And obviously you can do the same thing with side BC, because you know the angle opposite that as well.
Yeah. Yeah, you don't actually need the cosine rule at all.
And then you can half AB sine C and get your area.
Yeah. Did you get 21.5? What did you say?
Yeah.
Yeah.
Yeah, that's side BC. I worked out side AC first, which I got 32.2.
Yeah.
But I did that using the sine rule.
Well, absolutely. I would always use the sine rule as your first thing to try, because it's much more straightforward than the cosine rule. But obviously, just, it's up to you. There's often a number of choices.
Yeah, crazy.
Sorry, I'll just and the area. Alex, do you wanna? Have you done the area? Or have you wandered off somewhere, Alex? No, you really have wandered off somewhere. Okay. Anyone want to do the area? Jerry?
I've got half AB sine C, which is half times 21.5 times 32.2 times sine 26, which gives you 151.7 centimeters squared to one decimal place.
Is there some rounding? It might be this one.
I've rounded my inputs as well, so I've kind of cuffed it a little.
Yeah. So don't do that. But yeah. Otherwise, yes. So when I mark, if that's wrong, yeah. I mean, if it's just slightly out, you don't get that mark at all. You only get that mark for 2 marks.
You Nazi.
Well, I'm afraid that is the mark scheme. It is really
That's some
hard.
follow through, Mark. Come on. Have you had a follow through?
Yeah. No, follow through.
The mark scheme.
Yeah, actually, follow through is now a bit of a myth, really. It's so rarely used. And I was very much surprised when I became an examiner, because for years I've been telling kids, oh, don't worry, because they'll give you follow-through marks. No, they don't actually. They give you follow-through marks for the method. So if you still then use this and use the incorrect one there, you'd still get the follow-through method mark as such. So it's a method mark that you use the wrong numbers. You don't get follow-through answer marks, which I was very surprised about. So for example, if there are 2 method marks and it kind of goes method, answer. In fact, I'm saying that completely incorrectly, because the A marks actually stand for accuracy, and that's why you don't get them. If the M marks are method, the A marks are accuracy. So it goes method mark, accuracy mark, method mark, accuracy mark. You've got the first method mark. If you fail to get the accuracy mark, you might get the next method mark, but there are some of them that say if they don't get the first 2, don't give them any more marks. It's really harsh. And actually, I got we get marked, we get graded according to how well we do each year. And I've got down to a C this year because I was just feeling too kind last year and really got into a lot of trouble. So I'm really harsh this year. We won't do this because I want to get on to something else. But this is sort of much harder getting them to, for the ones that you really want to challenge, something you can just give them. Anyway, talking about radians now, and where this developed. I think we've talked about this before, haven't we? But actually radians came first because it's more natural. It came from the circle, and the definition of 1 radian is the angle that you get when the arc length is the same as the radius. So this sector, the radius and the arc length are the same, and it creates an angle that is 1 radian. And if we were, and I should have done the rest of it, because I think there is a nice little app that you can get where this sort of continues round. And if you can imagine the next length of the radius down to there, and in fact you can get the kids to draw it. If they draw any radius and then get a piece of string in order to go around the slope, so they measure the length of the radius, go around the slope that much to create the next radian, to the radian angle. Then they can do 2 radians, they can do 3 radians, and maybe they can discover, you can sort of say to them, well, how much is half your circle? How many radians? And they're going to be like, oh, it's 3 and a bit. Oh, 3 and a bit. Oh, I've got 3 and a bit as well. Oh, gosh, what does 3 and a bit remind you of? And maybe they might discover that 180 degrees is equivalent to pi radians, so 3.14 radians. The reason for it, based on this, is if we think about a sector, so an angle out of 360 degrees, and the circumference of, of a circle, we know that for this angle it's equal to the radius, the arc length, for that sector. And if we rearrange this, then that's how we end up getting that the angle equals 180 over pi, and that is what 1 radian is. So that was sort of all I was saying about radians. There are these formulae. So S is actually what we call arc length. I don't know why it's not an L, but probably because L represents length and not a specific one. So to get the arc length, it is just R times theta, which is the angle here times the radius to get. Sorry, this is for any arc length. This is not just for saying it's 1 radian, obviously. So for any sector of a circle at AS level, they're expected to do everything in radians, and they'll be finding arc length in the areas of sectors using these formulae, which they have to learn off by heart. But we're not going to dwell on that today. We're going to keep going because I really want to look at solving equations. Yeah, so the exact values we talked about were trigonometric ratios for angles of 30, 60, 45. And you can derive them by drawing either an isosceles triangle, which has got length of 1. You then calculate that the hypotenuse is √2. So if you look for sine, it's going to be opposite over hypotenuse, so that would be 1 over √2. So sine 45 is 1 over √2. Similarly, cos is 1 over √2. If you draw an equilateral triangle, all of length 2, and you split it in half, then you've got your 60s and 30s. You can calculate this, which is √3, and then you can sort of look at each one and go, okay, sine of 60, opposite over hypotenuse. So sine of 60 is going to be √3 over 2. This is just, it's not necessary, it's just useful as a way for the kids, if they cannot learn them just off by heart straight, to figure them out. In my head, I'm like, okay, I know that it's √3 over 2, 1 over √2, or a half, and I just try them on my calculator. And where I don't get, my calculator just gives me a number. So I get like 0.7070, and I'm like, oh, that's 1 over √2. Whereas I know that the new Casios give them in thirds anyway. So it's reaching a point now where they're trying to find ways of asking students to give these exact values without them being able to kind of cheat and use the calculator, but it's getting trickier. So that's just a table you can get them to then fill in, and that's just getting them to test their radians. So to convert between degrees and radians, we've got the fact that if we know that 180 is pi, then whichever way you're going, you can convert it. So if I want to know what a radian is, so 1 radian, which we do with a little c, I get by dividing by pi. If I want to go back the other way, then I need to do pi over 180. Let's get 1 degree. It's pi over 180. So to convert from 30 degrees to, I mean, obviously you can just see 30 is a sixth of 180, so it's just going to be pi over 6. Or you take it down to 1 degree like this, and you say, okay, so if 1 degree is that, so 30 degrees, so do this, times 30, and if I cancel that down, that's a 1, and that's a 6, and there's my pi over 6. So depending on which way you come at it, they do get a little bit confused about this until they really start using it a lot, and then they get used to what all of these are. Maybe I think actually if I click on my computer, no, there you go. So that's something that after we do it, I kind of have around, get them to make a poster of it or print it out and have it on the walls, so they get used to it, and so they can sort of look at it. But I don't want them to look at it too much, so they rely on it, but somewhere between. Oh yeah, so here is the bit I'm going to talk a little bit about. The area we get by considering it's an angle over the whole of the circle. So because 180 degrees is pi, 360 degrees is going to be 2 pi. So if we consider a portion, so one sector of a circle, it's going to be the angle theta over the whole of 2 pi. And the whole area is pi r squared. If we just take that fraction of it times pi r squared, we can cancel the pi's, and we end up that the area is half theta r squared, provided theta is measured in radians, because we're taking it over the whole radian measure. Similarly, for the arc length, and we normally do use a little s rather than the big one, the same thing is true. We times it by the circumference and cancel, and we get that it's just the theta measured in radians times by the radius. So they, again, that's just something that they need to know and use. So here's one for you to do. I'll write it up again. So area is half r squared theta, and arc length is just r theta theta. So have a go at just calculating this quickly. Oh, and you need to convert your, oh, you don't need to convert it really, because it's just a number. You don't have to convert it to radians, you're not using it. Just use it as a number. And put your hand up when you've done that. Yeah, Will, do you want to say what you got?
The arc length, I got 16.24.
Yeah.
And the area, 94.192.
Yeah. Yeah. So you don't have to go through this, you just jump straight to the however, of course, if the students have forgotten how to do it, it is fairly easy for them to derive it by thinking about, oh, it's still a fraction of the whole area and circumference. Is that all right with everyone? How would you find the perimeter of AOB?
I can do this one.
Go on then, Adam.
11.6 plus 11.6 and then plus 16.2.
Yeah, good. Students forget though, completely forget. Especially because in their head, perimeter and circumference kind of mean the same thing. They sort of think, oh, perimeter is of a circle, is the circumference of a circle. They forget that it just means, it's length round, all the way around, whatever shape you've got. Right, so thinking about moving away from just the kind of triangles and sectors into using the functions, the trigonometric functions. So sine, cosine and tan are, just like x squared and root x and x cubed, they are functions. And so we can draw graphs of them. And this is something that the kids find a little bit odd, because it's just the 4 being just a button that they press on their calculator. And for some of them, suddenly everything makes sense. And it can be useful to teach them. Well, they do need to know, in fact, at GCSE, what these graphs look like now. And to be able to do transformations of them. But I think they really get it a lot of the time. So they need to know about the functions. Use these identities, which we're going to look at. They need to know the exact values as they do at GCSE. And they need to be able to find solutions to equations. So here is the graph of sine theta. So it's always useful as your first thing that you do, and I think I made you do this, people who are there, is to get them to do a table of values, keep pressing, you know, doing 30, 60, 90, and then maybe doing it in radians rather doing it in radians, whichever one you know you taught first, and getting them to plot the sine graph so that they get a real feel for it being between the values of 1 and -1 and what's happening at each point. Same for the cosine, which is just a sine graph shifted, because it's just the what do you call it? Not converse. Cosine is the tan is different, and actually it's because tan is sine divided by cos. Because if we think about if I did this now, if you think about SOHCAHTOA, SOHCAHTOA, so sine of an angle, can't bother to write this one. Sine of an angle is opposite over hypotenuse. Cos of an angle is adjacent over hypotenuse. So if you think about tan, that is opposite over adjacent. And if I was to rearrange this, opposite, I would write as, that's facing over here, h sine theta. Adjacent I could write as h cos theta. Those h's cancel, leave me with the fact that tan theta is sine theta over cos theta. Being able to prove identities doesn't really come up at AS, but it does come up in A-level. I have done a whole PowerPoint about the trig at A-level as well, which I think I've uploaded to Student Central in the trig resources that go with this. But it would just, there's so much, and it's all the same sort of thing, just more of it. There's just a lot of trig. So periodicity is meaning the fact that it repeats. So the period of the graph is how far it goes before it repeats. So with a sine and a little thing, it's 360 degrees before it starts repeating. And because of this, we have the same solutions. We have more than one solution for an equation. For example, sine 30 equals a half. So if we go across at a half, we hit here, which is 30. Sorry, this is in radians. It then hits the next bit again at 180 minus 30, so 150. And then again 360 plus 30, so 390, and so on. It goes on and on and on. And that way as well, so minus 210. So there's all these different values for sine. So you will always be given a range for which they want the answers. The value that the calculator gives you is called the principal value. So the students should write that down always as their first thing they get. But it may not be an answer within the range that is required. They thus need to use that principal value to get the others, because as you can see here, the 30 tells us that we've kind of gone 30 in from that side, so we need to come 30 back from that side. But we will look at this a bit more. So at GCSE, they might, we don't really know yet, of course, what on earth is going to be happening with the new GCSE exams. But they could say, they could give, because they're expected to be able to recognise trigonometric graphs, they could be asked to read off something like this, off any graph. And they'd be expected, just as usual, to draw the line across and up and read it off. So the minus 0.3, x is going to be, I don't know, 200 maybe, not even 190. And I think the expectation in terms of teaching GCSE students about trig functions is this fact that were they to be given this, what they're looking for is to see, okay, yeah, you got that first answer. but can you go across and get that second answer? And are you aware that there'll be more than one answer, which is weird, isn't it, to them? Because so far, they've solved an equation and there's an answer. And we've sort of said, no, there is only one value of x, haven't we? That, you know, there is a correct answer. And this is where they've been associating equations as an algebraic thing that is separate to the functions. This is why I think it's so important from the beginning that you start to say, okay, solving a linear equation is because you've got a linear graph, and we're talking about where it hits a particular value. And solving a quadratic equation is, again, related to the graph. And thus, when they get to this point, hopefully, they're thinking, okay, solving an equation means looking at where y equals minus 0.3 and finding out what the x value is on that graph. Oh, there you go. I put, does anyone prefer to use cast diagram? I might have mentioned this last time. Does anyone know what a cast diagram is? Right. In that case, I'm not going to mention it.
Yeah,
Will?
I used the cast diagram. It's the weird graph, isn't it, that we've got where each one is positive.
Yeah.
So between 0 and 90, they're all positive. Between 90 and 180, it's only sine. Between 180 and 270, it's only tan. And between 270 and 360, it's cosine.
Yeah. So when
I've shown it to my students, but once they drew the graphs, it was like, you know, if we only know the shape of the graph, it's a bit pointless.
Oh yeah, and the thing is that so many questions actually say to them that they want to see a graph anyway, so you'd just be doubling up if you did this as well. When I was at school, we were really, I mean, I was taught what the graphs look like, obviously, but then we only used cast diagrams to solve equations. So for me, I started off, when I started teaching the cast diagram. And lots of the kids do like it. Lots of the kids are just like, I don't see the point where I can just draw the graph. So the cast diagram is used, as Will says, it tells us where the graphs are positive. So it tells you about the graphs as well, which is quite useful. They are all positive between 0 to 90. So if I next to it draw what's going on here, this is a sine graph. Oops, slightly uneven. Cosine, so cos crashes. So we sort of go sine soars upwards, cos crashes downwards from 1. And tan, oh dear, sorry. Well, that's just rubbish, because I was supposed to be putting them all in line and I just completely rubbished that. Okay, let's then post it again. Okay, we're trying to do this all in line. So here is 90, is the peak. Here, 90 is where they cross. Now, you know what I said before about tan being sine divided by cos? If we look at the values of what sine and cos are at 90, it's 1 and 0. If you divide 1 by 0, you get something that's not possible. And thus, we get an asymptote. So, with the kids, we don't often sort of talk to them about the identity until later on, but I think it's quite useful to explain why the graphs look like this. And the same happens again. See, the problem was that this was supposed to dip down here and there to the 180. So let's imagine this is actually crossing there. So 180 is where it crosses, and again, goodness me, at 270, we get another asymptote. Anyway, what this means on the cast diagram is, do you see here, this bit here, oh, can I have another one? at this bit here and this bit here, so between 0 and 90, all three of the graphs are positive. They're positive, well, x and y values, but they have, obviously they're positive y values. So this is the y value is positive. Between 90 and 180, sine is still positive for its y values, but cos is negative, and tan is negative. So between 90 and 180, only sine is going to be positive, which helps you when you do your principal value to figure out where the answer is. Between 180 and 270, cos and sine are both negative, but tan is positive. And finally, between 270 and 360, that bit, they're positive again. Now, what this means, solving equations. So solving equations, sine x equals 0.5. If you want to solve that, you have to undo it. If it was x squared equals 0.5, you would square root it. So in order to do the inverse, you have to basically turn this into x equals sine to the minus 1 of 0.5. So on your calculator now, that's generally, you get that by doing shift sine 0.5. Although on your old sharp calculator, it might be that you need to press 0.5 and then press shift sign, because for some bizarre reason, calculators used to do it in reverse. Oh no, on my this one it still says, my sharp one it still says do the shift sign first, which makes sense to me. So if you press shift sign 0.5 on your calculator, if it's in degrees, it will give you the answer 30. If it's in radians, it will give you whatever pi over 6 is. 0.524, isn't it? Lots of the students stop there. Even after you've gone on and on and on at them about the fact that this is AS level, you need to draw a graph or a class diagram so that they can think about it. So, depending on the range, there are many, many solutions. So, the most important thing is that they always have to look at what the range is as well. That's and then we can find all the other ones. Now, there they put the range as 0 to 360. So now, our first principal value is x equals 30. That's our first solution. You do your sketch and show you what things are. You draw your line across from 0.5 and down. You've got the first solution there, and then the second solution is here. 180 minus 30 because of the symmetry of the graph. And I think what I struggled with as a student, and why I never used the graph because we weren't really taught it, was that I couldn't figure out, and a lot of students struggle with this, they are like, wait, whereabouts is that? Do I need to add it to 180 or take it off 180? What am I doing with it? That's why, and I'm just going to draw it briefly again, that is why the class diagram can be helpful. If you find that you've got a student who is struggling to understand these symmetries, I'm going to look at it now and I don't know why I think so. But when we use the class diagram, we draw in the principal value. So here it's 30. Now I can see directly, because these axes are lines of symmetry, I can see that the other answer is there. So that angle there is 30. We're always measuring from 0 . So we want the angle that goes all the way around there. So we want 180 minus 30, which gives us the 150. So that's how the class diagram works. Does this make sense? Have you seen this before? Yeah. Alex, were you saying you have as well?
Yeah, I've seen it. But I've never seen the cast diagram.
Right. I won't keep on about the class diagram. We'll just move on, because if it's something, for me, it was something that's how I had learned it. So it was very straightforward to then teach it. Whereas if it's not, then it's another new thing for you to learn, which is fine. So solve the equation cos x equals minus 0.5 in the interval 0 to 360. Again, if you do shift cos of minus 0.5, you get the principal value as 120. Great, that is in between the region that we want. We sketch it, draw our minus 0.5 across, and when we go up, you can see the 120 is there. Again, by symmetry, we can see that we've had to go 120 in from the north, so we need to come 360 minus 120 to get this other solution here. So it's just getting used to that. That's 240. So, find the principal solution, sketch a cycle, depending on what the range is, basically, sketch that. So that it's really good actually when you do the sketching of graphs, because it means that they really get used to what the graphs look like. Draw in a line and find the second solution. So these ones are for you to do. So you've got cos x equals 0.5 and sin x equals root 3 over 2. So we'll do this one. Right, Adam, do you want to take us through the first one? Adam?
Sorry, I did it on mute. I did cos minus 1, 0.5.
Yeah.
And then, because cos starts at the top, I figured it's going to be from 360 take away 60.
Yeah.
So my first answer was 60, and then the second answer 300.
Yeah, good. Yeah. And make sure, of course, that both, we tend to sort of then write x equals 60, 300, to show that those are both the solutions, because often the principal value may not be included in the range, and so we kind of clarify again the answers. And Will, do you want to do the second one?
I did. So obviously sin minus 1 of root 3 over 2 gives you 60. And because the way the sine curve starts at 0, gets to 1 at 90, it's got to be 180 minus 60.
Yeah.
Will be the second one, which is obviously 120. at
Yeah.
60 and 120.
Good. Yeah. So that's the most. Oh, if I'm back to this. Do you want to take a break now and come back at 20 to 11? Okay.
Okay.
I'll see you guys at 20 to 11. Is that all right? Okay. I'll get this again. Cool. Okay.
Yes.
Good. See you soon. Right, put your hands up when you are back. So put your hand up when you're back. Just wait for Alex and Jerry.
You know, if they're not back, they're not going to hear you say, put your hand up.
I know. I do know that. Obviously, I can though equally tell who's back then. Yeah, what I should say is before you go. Hello. Good. Oh yeah, what I should say is in future is when you come back, put your hand up to show that you're back. Great. Okay, so in AS when you're teaching this, you've got options about whether you just teach it as one massive chunk or you break it up and keep coming back to it. I think I do a bit of both because otherwise it's a massive, very big chunk. You just find you're teaching just trigonometry for 3 weeks and then never again, and the kids completely forget. So like everything, it's best to sort of do it in bits. Now, this would still come up into the first section because this is simply just solving tan x equals 2. The first solution is 63 degrees, the nearest degree. You draw the graph to, okay, so they've put it here. Now it's really arbitrary because tan goes on forever, up and down. So it doesn't really matter where they put the 2, just as long as they then look and think, okay, so I've got another one there. So they had to go 63 in from 0. So here they're going 63 plus 180. And actually with tan, you always just add 180 because of the way that it repeats every 180 degrees. You're always going to just be adding 180 or if you're going negative and taking it away. So 63 and 243 are your solutions. So as it's saying, because the period's 180, you can always just repeatedly add or subtract 180, as I just said. So if you wanted it for larger ranges, you just keep adding. So luckily they don't really need to draw tan, but the thing is that once you go down that route of saying, oh, you don't really need to draw tan, then they're like, well, I know sine, I can do it in my head. So I generally just suggest do this. So have a quick go at doing this yourselves. Note the range, and that's the thing that the kids often forget. They just assume that it's always between 0 and 360. Right, who wants to have a go? Who's not had a go, really?
So I did it.
Okay, go on.
Although I came up with a positive number because this calculator won't let me do minus 0.5. I had to put in 0.5, which came at 26.5. And I've just guessed that it's a minus 26.5. And then I'm going to add 180 to it. And we round it up to 27. And then add 180 to get 153. The x is 153. 333. X is,
Yep.
X is minus 27, 153, and 333.
You're lucky that because of the symmetry of tan that does work, because for sine and cos, you have different answers for plus 0.5 and minus 0.5. Why are you unable to type? Sorry?
I don't know why it won't let me put in minus.
Yeah. Again, on old calculators, I don't know if you remember, you used to have to type it in first, and then you'd make it a minus. But let me see. How do I do minus? Do you have a +/- button?
Plus, yeah, I do. Yeah.
That's the one. Press that first. That makes it minus 0.5. So that will work now.
That's a chatty.
Yeah. But yes, you're right. You get 153 and 333. So right. I'm not sure why I'm going to this again. Oh yes, I know why I wanted to talk about this. Will, can you mute yourself, please?
Sorry.
So, if you type this into your calculators, solve this using a calculator. So you do shift sign of minus 0.5. You get the answer minus 30. Because if you think about the graph, it's gone back. That way, the calculator has gone back. It's gone to the nearest answer, basically, which is negative. And that's not in our range. Oh yeah, they suggest bracketing a value. This is off this is from A-level maths PowerPoint. I quite like that idea. I've never done that before, but they suggest putting a bracket around it so that the kids are saying, look, this is not part of the solution, this is just helping me to get that. And I quite like that. So the graph, so it's gone to the nearest one, which is here. But the answers that you need are both over here. So it's 180 plus 30 and 360 minus 30. Now, the kids, if they've left minus 30 on their calculator, that's fine. If they plus 180 though, they're going to get 150. So you've got to say to them, this is a value, just use the value, the 30. Don't worry about the sign. The sign is telling us that it's this value here. That we need to do 180 plus 30 and 360 minus 30. So that is their value, where they've gone minus 30 plus 360 because it's just the little jump. They've then taken the symmetry gives the second one. So just to be wary, the students really struggle with this. I think it just comes down to really knowing the graph and understanding negative numbers. It seems ridiculous, but they just sort of think, oh, I'll just use this number and add 180. And they get confused with the tan. They're like, I'll just add 180 to it. And you'll endlessly get answers of 150. So here's a couple more that start being negative, and have a look at the ranges as well. So have a quick go at doing these. So really important to draw a graph, especially for the first one. Sorry, you could try to do the second one. Cos x equals 0.65 and minus 180. But I've just realised that we've got quite a lot to do, so I'm going to start moving on. So your first value is minus 12. Great, that's down there. And based on what I showed you before, you're then thinking, okay, great, so I want to work out these two. But of course, it's actually saying between minus 180 and 180. So there are no positive solutions to this. They're both over here. The first one is your minus 12. And your second one is your minus 180 plus minus 12. I don't know why it's doing that one over there. No, stupid thing. No, it's not. Sorry. I don't know what it's doing.
Didn't it ask for it between minus 180 and 360?
I did on the cos one, but
Oh no.
yeah, but on that one I changed that one. But what I obviously did was I thought, well, I want to make it a bit different, so I'll change it. And then I totally forgot to change the graph. Right, must remember to change this slide. So what it's actually supposed to be doing is show you that actually need this one here. So the other solution, this is where the kids get really confused. So they've got minus 12 on their thing. If they add 180, then they get the right thing because they get, if they add 180, they get 168. But then they can kind of go, oh, okay, so it must be minus 168. If they take 180, they get minus 192, which isn't right, it's over here. So, in fact, to get it, I just do 180 and then type in the minus 12, so do minus 180 and add the 12 to get the minus 168 and use it as a value and not pay attention to the signs. The cos one is a bit more straightforward. Actually, I need to change that. You've got your first one. So 0.65, here we go. First one is 49. And the second one is over here. 360 minus 49. But because it's minus 180, you also need to look at this bit, which is silly, but again, actually pull the graph out. Because you've got this value here, where it comes down here. And where it hits there is going to be minus 49. And that's the third value. So that has got three solutions. Oh, okay, there you go. You get that bit there. You don't have to draw two graphs, so you just send that on that one. I think it's doing it this way to demonstrate the symmetries very clearly with this sort of kind of symmetry. So we've looked at just the basic ones. We've looked at what happens when your range involves negative ones or the principal value is not in the range. Now, notice here, I've got a sine 2 theta. This graph of sine 2 theta, if you think about transformations, what has happened to the basic sine graph? Can any of you tell me? Okay, can you tell me the name of any transformation? Okay. Here's the,
Stretch transformations and stuff.
yes, a stretch. It is a stretch. Okay, because what it's saying is every value that I have there of, basically, I mean, that's my x, my theta. In order to get the same value that I would have done if it was just sine theta, I'd need to halve it, because I'm now saying that it's 2 times that. So what that does is it stretches, although I'm more inclined to call it kind of a squish, because if we think of I don't know, theta being 90, so sine of 90 is normally 1. But now we're saying when the x value is 90, I'm actually doing 90 times 2, so I'm doing sine of 180, which is actually 0, which will be here. And in fact, what's happening is, oh dear, and in fact this goes on in exactly the same way. This value here is telling me how many waves now occur in 360 degrees. So rather than there just being 1, there are now 2 waves in 360 degrees. So the frequency has changed. Okay. So what that means is within any interval, instead of just having 2 solutions like we had before for 0.5, so originally I would have had these 2 solutions. Now I've got a solution there, a solution there, and this was if it was 0 to 360. And so I've got double the amount of solutions. Now what they've actually done is they've said from minus 180 to 180, which is fine. So the original graph would have just done this, but now the graph is going, that's what we're doing first. So between minus 180 and 180, extend it across this guy. It's still 3. There are still 4 solutions. There are these 4. Now, what we can do, we don't really have to worry about that very much. I mean, that is what is happening. But what we can do is just say, okay, well, let's x be 2 theta. So I'm still solving this same equation of when x is 0.5. However, because we're now talking about x being 2 theta, the range for x would be twice the range for theta. So we change the interval instead. So we're actually looking at it from minus 360 to 360. So you solve this equation as usual. So you'll get your 30, and then you'd get your next one So you just draw a regular sine graph. You'd get your 150. So as usual, you'd get your 30 and 150 between 0 and 360. And similarly, for your minus 360 to 360 going the other way, you get minus 30. Oh no, yeah, sorry. No, you get minus 210 and minus 330. I'd be inclined to draw the rest of it. But that is what 2 theta equals. So once you've got these 4 solutions in this extended range, you then halve them. And that then sits within your minus 180 to 180 range. So those are your possibilities. You can draw the transformed graph with the 2 waves in it, or more traditionally, we double the range and then halve it. Does that make sense?
You get sine a half. You get sine a half theta then. Is that
Yeah.
the opposite way?
So what do you think you need to do for that?
So that'll half the amount of
Solutions.
it will stretch it. It will actually stretch it, won't it?
Yeah, so it stretches it out. Yeah, like that. So it looks like that. Okay. And then, because there's only half a wave in 360 degrees. And as you go along, so here, look, you can see, yeah, here you can see, I say, as if this was an actually well-drawn graph. Although, that would be right. So look, the first solution would be 60, because it would be doubled, and the next solution, it's not, yeah, it's about right, isn't it? Look, 660 so yeah, it would, depends on, it depends on the range, actually. The best thing to do is, yeah, you halve the range that you had. Oh yeah, sorry, I haven't done that, have I? I need to halve the range that I had, rather than looking over here. Yeah, because that's not in my range, is it? So the original range I had was minus 180 to 180. So if I had a half, I would actually halve that to minus 90 to 90. And I'm not interested in any solutions that happen after that. And then to get, so I'd get the 30 and then I'd add it to get to double it to the 16. So yeah, you could get anything, any stretch. So, as it says, just the same for tan. So if you get 4 theta, multiply the range by 4, find all the solutions within that, and then divide that by 4. And here's a half theta. So they've got minus 360, so you need to halve that, minus 180, find everything in there, and then multiply them by 2. Now this one is a bit different. It's a translation. So all the angles have been moved by 30 degrees to the right. And thus the same thing happens here. All of these, you need to change the range by taking 30 away from it. So it'll be between minus 30 and 330. So you just find all the solutions within that range, and then you do this back to it to get back to theta. So again, I mean, this is just the next step up in terms of what they have to do. So find the new interval, find all the solutions, and then convert them back to theta. So have a go at doing this one. 2 theta equals 0, cos 2 theta equals 0. Yeah, Adam, do you want to have a go?
Not really, I think I've got it wrong.
Oh well, that's even better. What did you do?
I think I've got 120. I did cos 0.5 and then doubled it to get 120.
Oh, right. No. Do it the
Can't
opposite.
do that.
No. Well, hang on, let me just work out what the answers are. So, shift cos of 0.60, isn't it? Yeah. No,
So I got 120.
no, you're going the wrong way. You're going the wrong way.
Right.
Double the range.
Yeah.
So
0
you
to
find,
720 then.
yeah. So your initial answers are going to be 60 and 300. And then again, you're going to get, what's 360? 420 and 60. Is that right?
Yeah.
And then halve those.
Right.
So, no, I've not got that quite right, have I, in my head, in my calculations, but 60 and 300 the first ones. We then sort of go round again, so that the next ones are 360 plus 60 and 300 plus 360, or I could give it a 720 minus 60, doesn't matter. So those are our values in our new range. To get back to the old range and theta, we need to divide by 2. So should, yeah, so should be like that.
Right.
Does that
I
make
know I
sense?
got it wrong. Yeah.
Well, it's good anyway, you know.
This just seems like a really long-winded way of going about things. If you just use simple algebra, if cos minus 1, 2 theta is half, then given that cos theta is half, then cos 2 theta is going to be half of whatever that answer was. So you're going to get straight to 30, and then you just plot in where your 30s appear in your original range. Is that just not a quicker way of doing it? Or am I going to come up?
You'd come across by doing that.
Because I get exactly the same answers. Sorry?
A lot of the kids come a cropper doing that. I'm not sure
But it's
why
not wrong.
exactly. Yeah, I mean, if you really, you know, you're really switched on, you know what you're doing, it's fine. Why do they get one?
Well, here's the thing. To find out what that figure was going to be that we're going to slot into our range, we didn't do inverse cos 2 something equals half. We just did cos to the minus 1 half equals 60, and then we started messing around stretching the range. But if we were given cos 2 theta equals a half, then having worked out that cos minus 1 of a half is 60, then we could work out that cos theta was going to be half.
Oh yeah, sorry. I mean, once
you know that cos theta is going to be 30 now, then you can just drop your 30s in wherever they appear. So I'm not explaining myself very well.
No, you are, but I don't think it works because otherwise, because 2.
I'll take exactly the same answers.
So you've just gone straight to that. So you've gone theta is 30, and then you've got your graph of this, and you say, okay, so I've got theta. But wait, your graph that you're drawing though, you're drawing 2 theta then? No. Theta equals 30.
Let me get back to it. And okay, that's why I was asking whether there were any pitfalls to doing it that way.
There are, because I don't think you're going to get all the solutions. Because if you've just gone back down to 30, you're only going to get 2 solutions, aren't you? What does your graph look like?
My graph had twice as many Well, it had twice the frequency, but within the range 360. So rather, because what you've done is you've gone out to a range of 720, and then you've halved all the figures that you got, putting your 60-degree intervals into your 720 range.
Yeah.
And then you've halved them, get 31, 52, 10, 330. What I've done is, that's it.
Oh yeah, no,
double the
no,
frequency.
yeah. No, that's the other. Yeah, that's what I normally do too.
Cos 2 theta's half, then cos theta's
Yeah.
going to give you a 30-degree interval.
Yeah, no, that's absolutely fine.
Chuck that in.
Provided you have
Okay.
halved the, you've drawn the, so you've drawn the graph of cos 2 theta. So that's absolutely fine.
Yeah. Okay.
Yeah, no, that's exactly the same. We just tend to do it. Well, I do tend to do it this way. You're right. I always drew the transformed graph. No, that's exactly the same. If you're going to draw the graph of 2 theta, that is fine. Obviously, that's exactly the same.
Okay, cool.
Yeah, no, that's fine. So yes, either way is doing the same thing.
I just figured that if you could point out that the graph would just double in frequency, then it just becomes easier visually for them to see what they're doing. Otherwise, I can just see them asking, well, what, if the range you're given is 0 to 360 degrees, what we're doing bugging around with, 720 degrees.
I know. And I think you're right. I think I have a tendency to do it like when I showed you, in fact, when I showed you when I was doing it on the sign, I was drawing a double one. I also do that. But then this is kind of the more accepted method. And I think the reason for that is they don't have to think, do they? They only have to know how to draw the regular graph.
Okay.
So it depends on the students. So if it didn't give you a nice 30 or a 60, and you are asked to give them the exact fraction of pi. So for example, I can see for this, we're now getting into radians. So we've been doing everything in degrees, we're now into radians. You've been given this. They don't want to see you write some weird, or whatever it is in radians. They want to see you write that the principal value is pi over 4. If you do shift cos, so first of all, first thing we have to be able to do, and you have to be able to show the students, is how to change your calculator into radians when you're solving these. They can do it all in degrees and convert it, but they're not expected to. They're expected to be able to use their calculation radians. And it would just be so, I think if I was marking it, I'd be like, oh really, they did it all degrees? Because they should understand that radians, it's like when you speak French and you're endlessly like saying it in English to yourself and then translating it. They should be getting past that to thinking in radians. So they don't have to translate, they just think straight into it. So initially they will be translating between it. But really they need to be able to convert your calculator. So it depends on your calculator. I'm just trying to find mine, where it is. Oh, mine's in setup. I've got something called setup. So in setup, no, that's not helpful. I'm just trying to figure out what's going on here. No, not that one. I'm on my sharp calculator. So on my Casio, it's fine. On my graphical calculator, I just go into my setup and scroll down where it says angle. It's currently in degrees. I want to change it to radians, which is F2. Now it's saying rad instead of degrees. So you want to see something saying rad instead of degrees. Now, when I do shift cos of 1 over root 2, well, I get naught in fact, because I've just done 1 over root 2 without brackets. No, so if I was to just do it on my calculator, I get this 0.785 or whatever. They don't want to see that answer. They want to see an exact value. Now if I do shift pi divided by 4, I mean that's how I always remember it, I just basically do it and go, oh good, it is pi over 4, because that gives me the same answer. So you need to be able to convert it into radians, but you also are expected to just not even have to use your calculator for this, and be able to just write down that the principal value is going to be pi over 4. Yeah, and as it says, if you don't remember the fractions, use your calculator and degrees and convert to radians, and that is obviously possible. So you get 45 and then you convert it into pi over 4. And then it says if an exact value is not required, switch it to radians and you get that. So tan 3 theta equals 1 in between 0 and pi. So yes, your option is that you can either draw tan 3 theta, or you can draw tan theta and extend this between 0 and 3 pi. But the use of the pi, as it says in the range, tells you, I mean that is the only thing that tells you that you need to use radians. The students get in a pickle, not really paying attention, start off, I mean the first thing that you should always say to them is, the first thing to look at is the interval. What is your range? Okay, and then is it in degrees or radians? So they are doing the same thing we did before, where we extend the range. Tan 3 theta equals 1, so shift tan of 1 is something you should know, or you can do it in a calculator and compare it or convert it, but it's pi over 4. So because we normally just keep adding 180, in radians it's the same, but you just have to add pi. Now this is where the students and their ability to do fractions starts to let them down. So they've sort of, I see the answers and they've written pi over 4 plus pi plus 2 pi, and they often just leave them like that. They need to have collected them together though. And you're just like, come on, it's a quarter plus 1. So you've got 5 quarters, so you've got 5 pi over 4. What is so hard? I don't know. They tend to sort of leave it like this, and you want to see it brought together. So, you know, it does seemingly tax them a little bit in their fraction usage. So yeah, and then yeah, you're right, Joey, because the issue is, of course, that you could forget to do this, forget to divide through. But I think this is something that the kids can do a bit more mindlessly, I'm afraid, which kind of gets something. Here they're starting to find it all a bit trickier. So translations, when you're adding something on, yeah, so you just deal with the cos and leave this bit to one side. So it's still pi over 4, which is obviously quite nice because we've got pi here. So they're saying, okay, let's extend the range by adding pi over 4 to each bit. And when we solve this, our principal value is pi over 4. So if we draw our cos graph, here we go. Now, in fact, we've slightly extended it now, so we're going from pi over 4 to 9 pi over 4. So the first solution is pi over 4. There we go. The second solution is 2 pi minus pi over 4. Again, I struggle with that. You've got 2. If you write it in quarters, you've got 8 quarters minus 1 quarter, so you've got 7 quarters, so you've got 7 pi over 4. And if we want to see if we can get the third solution, So pi over 4 plus 2 pi will just be over here. Obviously, this is going to be 9 pi over 4. That is still just within the range. That is the top of the new range. And so our solutions are pi over 4, 7 pi over 4, and 9 pi over 4. We then want to take pi over 4 away from all of those. So we end up with 0, 6 pi over 4, and 8 pi over 4, which is in fact just 3 pi over 2 and 2 pi. Does this make sense? It's quite difficult to see it when you're not actually doing it yourself. And also when this graph is so rubbish that it doesn't do it. Any questions? It's all the same principle. Alex, you're good.
I think it's quite difficult for me to visualise it, and I think for me I would have to do lots of different graph work.
Yeah.
Plug in the values to see actually what's happening and to see where the values were in order to get a true grip of it, you know, and to be confident with, you know,
Yeah.
take it further.
And I think part of this, and I was just thinking about this actually, Jerry, going back to what you're saying about the way you've done it. When I used to use the cast diagram, of course we weren't looking at the graph, so we couldn't double up the graph, and it just meant that you just go round and round the cast diagram. So I think that's where that came from, because there was really, it used to be that you just use the cast diagram because it's the shorthand way of doing it. I think it was devised to enable a shorthand way of doing it. And all you do is you draw in your two solutions, whatever they may be, for example, and then you just go round and round and round, however many times, and do it that way. Right. We've just got more of the same. I think I want to get past this. I'll leave all these for you guys to muddle through at some point. But it's the same sort of things. You just have to be aware of the range. Let's do that notation. Because they didn't do exact answers, so this is where you're using your calculator in radians. So the first solution they've got here is minus 0.4, which is quite similar to that, which is quite one of those things that's bound to cause confusions with the kids. How is that right? Got no sort of concept with yeah, that is the problem they do have. With radians, they've got no real sort of concept of the size of the value they're looking for. You've got to sort of say to them, well, come on, pi is 3.14. So, you know, that's going to be about 1.5-ish there, isn't it? So, you know, that looks about right. So here we've got our different solutions, but I'm going to zip through this and leave those deuces because I want to get onto, oh yeah, I want to get onto this. Right, sine squared. Sine squared actually means sine x all squared, as it says here. So, what you've got to think to yourself is the graph of sine x all squared, we can't draw. We don't know what that is. So we are really coming at this from an algebraic point of view. And we've got to be aware that we've got kind of sine x equals a quarter. So there's sine x times sine x equals a quarter. So there's two solutions. We square root it. We've got sine x, and we've got the plus or the minus of root a quarter. Really important to remember that. This is bringing in their knowledge of quadratics into their trig. So you've got two different equations to solve, basically. You've got when sine x equals a half, and you've got when sine x equals minus a half. And that's what you do. You split them and you write them as two bits. Kind of on the page like this, we do this. We go down one side and then we go down the other side. So sine x equals a half, so shift sine of a half is just 30. And so, yeah, as it says, we've got two simple trig equations that we can just solve the usual way. So when it's 0.5, we've got 30. What's our range? Minus 180 to 180. So we have got 30 and 150. Then we've got sine x equals 0.5. Sorry, minus 0.5. So we know that that's minus 30 and minus 150. So we have four solutions to our original equation of sine x squared. We've got minus 150, minus 30, 30 and 150. The kids do all sorts of things, as you can imagine. Mainly they just square root it and just solve the half. They forget that there's a plus or a minus. But they do all sorts of things. And in fact, it gets more complicated. So here we have 3 sine x squared, or sine squared x, plus sine x equals 0. If you think about this as a quadratic equation and call the sine x s, then we can write this as 3s squared plus s equals 0. Now you can see that it's like a quadratic. And we would solve this by factorizing out the s. There you go. If there's no common factors, use the formula to do the square. Well, in these situations with trig, I really always factorize. Otherwise it'd just be such an extra fact. So we've either got that s equals 0 or that 3s plus 1 equals 0. And those again are our two things. So we go back to what those mean. So either sine x equals 0 or, solving this little bit, sine x equals minus a third. Then x is going to be sine minus 1 of 0. So it's going to be 0 and 180. Oh, what's interval? Yeah, 0. Oh, 0 is always one to watch. Okay, because for the sine graph, it's 0 at 0, 180 and 360. So there are actually 3 solutions to that. Sine x equals minus a third, they'll just be the 2 solutions. Here we go again. So this is a sketch. 0, 180, 360. Sine x minus a third, the first value is, there. Look at this minus. So it gives us the nearest one, which is there. That's not within our range. So we need to take the values and, well, add 360 to it to get that one. And then do 180 plus the 19.5. We have 5 solutions to the original quadratic. So those 5. Does this make sense?
Bit tricky for me, Sarah, if I was being honest.
This is really tricky.
But nothing that I couldn't, a few weeks studying it wouldn't probably sort it out.
And the kids do, you do spend a couple of weeks doing this. Well, the thing is that you spend a lot of time just on the basic ones because they get, stuck on the basic ones. By the time they get to quadratic ones, well, obviously they do not sit for 3 hours like we are doing and just do every single type. This is really, really hard work on the brain, especially on a cold and wet, windy day when you just want to be. So
how long would you take teaching this? How long would it be?
15 lessons for all of the trig.
15 lessons. 3 lessons, right.
Yeah, well, yeah, so 3 weeks, 4 weeks. No, maybe maybe that's probably, might be extreme. It's difficult because you don't tend to do it like this. You don't just like pile it on them. You do a little bit of it, and you do something else,
Right.
And then you come back, and of course you've got to run over the last bit and then build a bit on it, like we do. I think they'll find it too intense. I think I tend to do, so each lesson I introduce a new thing. So the first lesson, you'll just be doing radians and like arc lengths and sectors. The next lesson, well, in fact, what I tend to do actually is you do a load where you just do solving the basic equations using degrees. Oh gosh, I'm just thinking this through actually. I've done it in very different ways depending on how I feel about it. Sometimes I teach them everything all in degrees. Then we teach them radians, and then we go, okay, all of that stuff that you did in degrees, you can now do it all in radians. So you can either do that, or you teach the radians first, and you do them doing both at the same time.
What's a good scheme of work for this then?
I think I'm inclined to say, do it all in degrees so they understand and can see what's happening. I think I tend to start this module, because often this is in the C2 module, so the second core module, and I'll start with solving these equations. So we start with doing the graphs of them. It's kind of a reminder from GCSE. What are the graphs? Learn these graphs. Let's solve some basic equations. And then after that we go, okay, now let's solve some of the more complicated equations. And it gives them a reminder of transformations. So we do transformations, we do stretches, and then bring that in, bring it. So you kind of do a bit of, because transformations is part of the topic too. So you do a bit of something else and bring this in. And then we talk about trig identities, which I'm going to do a bit in a minute. And then we bring in radians and then kind of do it all again in radians. But I often do that at the end. So we do it all in degrees, and then we might go off and do some logs and exponentials as for something different, so that when we come back to it, we then learn radians and do something else. So yeah, I think one new thing a lesson probably works quite well. We do find that quite a lot of them just don't get it from the outset, and they're kind of always falling behind. Right. Now, we can only solve this. I've done the clicking on here. We can only solve it once it's like sine theta equals something or cos theta equals something. We can't do it if we've got one that involves sine and cos like this. So if we've got this sort of quadratic, so this is a typical exam question, something like this. Oh gosh, the kids, well, they're probably just filled with horror. But then they're going, I have no idea what I'm supposed to be doing. They don't seem to recognise that they have identities that can help them with this. So we need to be able to, they have to learn two identities. Identities are things that are always true. We have the Pythagorean identity. Cos squared theta plus sine squared theta equals 1. And again, you can get them to derive this. It uses just a right angled triangle like I did for the tan one. You don't have to use the identity symbol, they can just use the equals. It doesn't really matter. No one's going to care in the exam. What this means is, when I look at this, I want to change it all to sine or all to cos. But I can't do anything with that cos. I don't know anything that I can replace that with. But the sine squared theta, I could rearrange this so that sine squared theta equals 1 minus cos squared theta. And I can replace that in there. And then I'm left with a quadratic that is all in cos. Being able to see that is fine for me. For the students, it's really difficult. And unfortunately, these questions are ones that are just left completely unanswered because they don't know where to start. So that is sort of the problem with these. So here I've got this. I'm going to turn this around so that sine squared theta is 1 minus cos squared theta. And then I'm going to substitute that in here. So I get 3 brackets 1 minus cos squared theta. So I've just replaced that. Plus 5 cos theta minus 5 equals 0. I multiply out this bracket so that I can start simplifying things. I've got 3 minus 3 cos squared theta minus 5 cos theta minus 5. Now, what they say in this is just let it be a c or an x or something, some letter, and just do it like it's a regular quadratic. So I don't do that. Personally, I don't do that. I tell the kids about it, and some of them do it. So if we rearrange all of this, we end up with bringing the numbers together, and then I think we're going to make it all positive. So we'll make it 3c squared minus 5c plus 2 equals 0. This is just a regular quadratic equation. And the next step is to factorise it. That factorises into 3c minus 2 and c minus 1 equals 0. So either 3c minus 2 equals 0, so c equals 2/3, or c minus 1 equals 0, so c equals 1. So all of this stuff that came before is just extra fluff, basically, that needs to happen in order for you to get to a basic trig equation that you can solve. So these are actually much nicer. I would rather see this than one that involved a stretch or a translation, because you don't have to faff about with anything. You're left with just a very basic thing, but you've got to do a quadratic before. And so if they struggle with quadratics, then they're screwed, basically. So, but this is quite good because it does refresh all the quadratic stuff. So for this first one, cos theta equals 2/3. We've got theta's 48.2. Can't remember what the interval was, but we draw our graph, work out the other one, and get our two solutions. Then we've got the cos theta equals 1, and that's very nice because that's just north of 360. So those are our 4 solutions. Common mistakes are that they only do one of them. They might factorise, often they factorise and they get c equals 2. You can't have anything bigger than 1. And they just say, you should put a line through it and say, not possible. So it might be that part of your quadratic that you end up with is not possible anyway. So there are still only 2 solutions. The other trigonometric identity they need to know is the one that I told you before. Oh look, they're actually going to prove what I showed you earlier, which is that tan theta is sine theta over cos theta. So they've got 2. The Pythagorean identity is sine squared plus cos squared is 1. This one is tan theta equals sine theta over cos theta. In order to get the kids remembering which way up it goes, you could write it this way. So sine theta over cos theta equals tan theta. And then it's like it used to be kind of SOHCAHTOA. It's the same order, the SOHCAHTOA. But ultimately, again, they could go back to this triangle and figure it out. By thinking, oh, tan is opposite is adjacent. So that one's got the opposite on the top. So the way to recognise these, so if I just go back to this one, this has 2 different trig ratios in it, but one of them is squared. That tells me I need to use the Pythagorean identity to get rid of that bit and change it. This one we're now looking at has 2 different trig ratios, but neither one is squared. And I need to get something that involves sine over cos. To do that, I just, as you can see, if I divide both sides by cos, then basically we notice there are 2 trig ratios with no squared term. You mustn't, oh, and I see so many kids do this, you mustn't square root the Pythagorean identity. It does not square root. That is not true. Pythagoras did not say if we do cos theta plus sin theta, you get 1. So you see a lot of that rubbish. And a lot of kids, basically, they're like, oh, there's a minus, let's bring it over the other side. Okay, so I've got sin theta plus cos theta equals 0. Okay, that's very nice. How is that going to help me? Divide through by cos theta. So we get tan theta equals minus 1. And that, again, is just a simple trig equation. Oh, sorry, did you just come back? Was that from the mute? So, this one's just saying do it in radians. Should really be pi over 4. So minus pi over 4, add 180, which is pi. So 3 pi over 4. So with a quadratic equation, if there's only one trig ratio, then you just factorize and solve the resulting. If there are 2 trig ratios, you use the Pythagorean identity. If it's not a quadratic equation, then you use the tan theta equals sin theta. So that's been fairly intensive, sort of the most complicated bit. And as you can see, the main problem is if the kids can't use these or do the quadratic bit, then they never get to their simple trig equations. And they might be really great at solving basic trig equations, but they never get to it, which is a bit of a shame. So yeah, they need to be sort of really spot on with these to get to that. So your turn. Have a go at doing this. I will write out for now the Pythagorean identity because I will just hold it to you. The kids need to learn this. One of the key things they also forget is that, to solve a quadratic, you need to make sure it's all on one side equaling 0. So they forget all their quadratic stuff as well. A common thing that the kids also do is because they'll have been working in radians, if they're then given something in degrees, they don't think about what things should look like. And so like I've just done shift sine of 2/5 and I've got 0.411 and so that has told me, whoops, my calculator's in radians, because that would be a ridiculously small answer. The kids don't always realise that, and you get loads. You really need to get them thinking, does this make sense? Does this make sense? Is it in radians or not? You put your hand up when you're done. Anyone wanted their answers? Can we reach the end? There's probably a 5 or 6 mark question exam, so I guess you'd expect to take 5. Yeah, I'm really struggling to get to
I can get the first bit, but I can't get it after. I've rearranged it so that cos squared theta plus sine squared theta. I rearrange that so I get cos squared theta equals 1 minus sine squared theta.
Yeah.
So just rearranging that. And then plugging that in for cos. So substituting it back in.
Yeah.
And then I've got 5 brackets 1 minus sine squared theta bracket equals 3 sine theta plus 3,
Mm-hmm.
and then I'm lost.
And then you've got to, okay, so then you multiply out that bracket you've got. So 5 times 1 is 5, and 5 times minus sine squared theta.
Okay.
Yeah, and then you can bring the numbers together and
Ah,
put it all on one side. So put it all on the positive side.
okay, let me try that.
Has anyone reached the end? Yeah. Okay. They're very involved, aren't they? You can see kids losing the will to live in the exam. So, have you managed to get to that? Talk, I'm very quiet.
I never got the bottom bit. I got 5 minus 5 squared plus 3s, so that's it.
Yeah, so,
And then what happens?
so factorize, and then we've got this bit equals 0, so rearranging we get s equals 2/5, so sine theta is 2/5. Sine theta equals minus 1. You solve each of those just as we did right at the beginning, and you end up with 3 solutions. So I'm just going to go through that. It isn't this bit though that is hard, is it? It's the getting there, and unfortunately we can't get there. You don't get anywhere, and the students need to be able to do this whole thing in 5 minutes. But I have had lessons where they maybe do 1 in the whole lesson, because yeah, I don't know what you guys think, but it's fairly hard. It's just it's made up of so much stuff, isn't it? So there's a lot going on just to get to get to that. So here is another one. What's the time? Basically coming to the end. This one is the same thing, but it's using the other trig equation. So rather than bothering to solve it as well, just see if you can rearrange it so that you got it in terms of 1 trig ratio. Exactly, added difficulty when you load in. So, don't use this one. Simpler than the quadratic one, and yet I find that more kids seem to make errors. They just don't seem to remember this. And a lot of them end up like multiplying by like a sign, so they've got a sine squared, they've got cos sine here, and trying to figure out why they can't get it right. So if you divide through by cos theta, you should just end up with sine over cos is 2, so therefore tan theta is 2. And then you can just shift tan of that if your calculator's in radians, and you should get 1.11 radians. It's about 63.4 degrees. And if you add 180 to that, which is adding pi to it, then you'll get 4.25. 2 pi is about 6-ish, so that's going to be it. Oh. Questions?
Wow.
Have I just like, you need to go down, have a lie down now.
Could we do this tomorrow again?
Feel free, you can do this. It's all uploaded to the Student Central, and you can work through this and the recording and try and do some more practice, which is definitely what it needs, isn't it? I mean, you know, seeing all of this very, very intensely in just this time here is all well and a lot. And it's one of those things, and I mean, it's like everything, whenever you teach anything that you've never really come across before, it's going to take you at least 3 times of teaching it before you really get to grips with it. So, you know, have a bit of a practice. You've got to self-study, actually. Let me just go to Student Central. So your next, let me drag this up as well. Here's the plan. We are here at the scheduled task. It really feels like there's not very much, I'm really not seeing you guys very much this year. I suppose it is like that, isn't it? We're all higher studies last year. So you've got a self-study 1st of February, which is doing this. Let me check that I definitely put that all on Student Central. I thought I was really organised.
I've actually bowed out of teaching A-level.
Well, fair enough.
Enough's enough.
What had you done?
No, I just, before they was going to go in there, I said, look, I don't want to risk your students at all, so something in the future.
Yeah.
Something way in the future, but at the moment, not a chance.
Don't, yeah, just don't get to the point where this is so far away from when we've done it that you're like, oh, I could never get back into that. I mean, obviously, I know that you're not really into it yet, but if you see what I mean. Oh, I've not put it on there. Right. So.
Well, no, I think the school's going to give me a job.
Oh,
and they're
okay.
quite supportive, so they're going to say, well, next year, come in and do the help with the further maths. So they've got like a progression for me. So come in and do the further maths, and then the year after that, he's got like a 4-year plan for me, really. So which is really good. I was really lucky. Yeah.
When you say further maths, you don't mean A.
Further maths. No, the FSM pure course.
Oh,
is,
okay, the add maths.
in between, yeah, in between.
Oh, sorry, there is a further maths episode at GCSE. Yeah, right.
Yeah.
Yes,
So
exactly.
that one first, and then the rest of it. So that's the way ahead.
So this is today's webinar here. What have I done? Oh, it's just the PowerPoint that we're doing now, and and then A2. For those of you that really fancy doing some more of this, these equations get harder. There are even more trig identities. So if you want to do that, then feel free. But I realise I haven't given you lots of practice there, but I thought I've obviously forgotten to put it on. And what I'll do, Alex, is that you message me your address and confirm when you have got permission to miss this. This is all the stuff. This is the stuff that goes with the pack that I will send you. If you work through the PowerPoint, that's there. So currently, you guys can't see it because I've uploaded it, but I hide it until we've done it. What I need to find is the self-study. So I haven't uploaded it, but I will do that now. So here we have solving these equations. So there's lots of practice on this self-study about converting and then solving. Okay, so I'll upload this and then you can practice that. Let me stop the recording.